Let's consider something called the pendulum. What's a pendulum? Well, it's essentially like an old grandfather clock going back and forth, swinging back and forth. We consider it in the simplest case of a mass, also called a bob, attached to a thin rod. So here's your mass M. Here's your thin rod of length. I'm going to use a capital L, even though the book uses lowercase l in a problem that you did in the section about linear approximation. So what happens with this? Is it attached to the ceiling? Is it attached to something else? I'm not going to worry about what it's attached to. I'm just going to imagine it's attached here stationarily, but it's allowed to swing back and forth. Okay, so this is going to swing back and forth. If the oscillation is small in amplitude, if the angle that it makes as it swings back and forth is small, you can come up with a formula, an approximate formula, for the period of the motion. The period, often called capital T, turns out to equal 2 pi times the square root of L over G, where again, L is the length of the rod, and G, as usual, is the acceleration due to gravity near the surface of the Earth. This is the small amplitude period. If the amplitude gets large, this formula is really no longer a good approximation. If the angle is too large, like if there's no ceiling above it and it's allowed to swing up here, if it's very close to the peak, it could stay up there for a while before it swings back down again. And the period would be very large and this formula would not be valid anymore. Let me write this without a square root symbol. Let me write it with powers. I'll write it as 2 pi times L to the 1/2 times G to the -1/2. Okay. Before I do some calculus with this, I would like you to think with me here about why this makes some sense. If L is large or gets larger, if you make the thin rod longer, imagine a very large thin rod here. That's going to cause this period to get larger, which corresponds to slower motion. A long period corresponds to slower motion. That should make some intuitive sense. Got a really humongous pendulum, it's going to move back and forth kind of slowly. Whereas if L is smaller, a very short pendulum, it's more likely to move back and forth fast. The period will be smaller. That's a more rapid oscillation. G, of course, near the surface of the Earth is about 9.8, technically approximately constant, is different. If you go up to the top of a mountain, it gets smaller. Or if you go to the moon, it's smaller. How many of you will go to the moon? Probably none of you, but if you did, it would be smaller. If you went to Jupiter, it would be larger. Pretty much for sure, nobody's going to Jupiter. But if you did, it would be larger. G is affected by how big of a planet or moon you're on and how close to the center of that planet or moon. So yes, it is smaller at the top of a mountain than it is at sea level. Notice G is in the denominator here. So as you increase G, like you go from the top of the mountain to sea level, the period will decrease. The motion will be faster at sea level than it is at the top of a mountain. Period decreasing is a faster oscillation. Anyway, what can we do with this with calculus? We can do linear approximation if we want. Let's give this function a name. F of L comma G, if you like. I'm going to use Mathematica, and so that'll be convenient. I can think about finding approximate changes in the period. Delta T meaning change in the period. Change in the period using linear approximation. And I can imagine it in this two variable situation. I can imagine changing both the length of the thin rod, and also I can imagine changing G by going up or down the mountain. In multivariable calculus, you can do linear approximation with both variables at the same time. By the way, you might wonder how the mass affects things, and the answer is for small oscillations, it really doesn't matter. That's kind of amazing. What's the formula? It's analogous to the formula for linear approximation in one dimension. The total change if you're only changing one variable, is the rate of change, the derivative, times the change in the independent variable. We've used that before. I'll say it again. The change in the dependent variable, in the case of one variable changing, is the rate of change, the derivative, times the change in the independent variable. That's analogous to distance equals rate times time. Except in this case, it's change in period, in seconds, say, equals rate of change of period with respect to one of the variables times the change in that variable. I'm using partial derivative notation here because I've got two variables. I'm going to use two different derivatives, and I'm going to imagine changing both variables. I could change L and find the rate of change of the period with respect to L and multiply times the change in L. And I could change G. I could find the rate of change of T with respect to G and multiply times the change in G. If I'm going to use this formula, I'm going to have to find those derivatives. It's easier to think about it with the exponents than with the square root symbol to find the derivatives. When you take the partial derivative of this thing with respect to L, treat the G like a constant. Constant multiples, when you take derivatives, just get carried along for the ride. They just stay there. The only thing you have to differentiate is the L to the 1/2. Use the power rule. Bring down the 1/2. 2 pi times 1/2 is just pi, right? The 2 and the 1/2 would cancel. And then you would subtract 1 from that exponent. 1/2 minus 1 is negative 1/2. The G to the negative 1/2 just stays as it is. That's as if it's a constant. That gets multiplied by the change in L. Now I add the derivative of this with respect to G, treating the L as a constant, and multiply that times delta G. Treat the L as a constant. This 2 pi L to the 1/2 would be a constant that just stays there. Differentiate G to the negative 1/2. The negative 1/2 comes down in front. 2 times 1/2 cancels, right, to 1. The negative sign stays there, though. I get negative pi L to the 1/2 G to the negative 3/2, because negative 1/2 minus 1 is negative 3/2. And yes, plus or minus is the same as subtracting. I could write this as a subtraction. Maybe I'll go ahead and do that. Pi L to the negative 1/2, G to the negative 1/2, delta L minus pi L to the 1/2, G to the negative 3/2. And I realized I forgot something. I forgot my delta G times delta G. Let's use this with a numerical example now. I'll use Mathematica to do this. And I'll type this in as a multivariable calculus function. F of L, comma G. I've got two independent variables. I'm defining this function of two variables. I need underscores when I first define the function. I'm looking at the original formula up here. I'll go ahead and type it in with a square root just to illustrate that I can. 2 pi, I make a pi by doing escape key escape, times the square root button here on the typesetting palette. I'll type L over G like that. Entered. I can re-enter this without underscores to see that it's entered. It's now stored in Mathematica's memory. Let's confirm the derivatives are right. If I've got two variables, it's better to use the D operator for the derivative rather than a prime, because if I did a prime, like, well, what does that mean? What am I differentiating with respect to? So I use the D instead. And then after the function goes in there, I just specify what the variable is that I'm differentiating with respect to. So if I put a comma L, that's going to find the partial of T with respect to L. I should get this. Maybe written with square roots instead of powers. I'm not sure. Yep. Okay. Pi, there's the pi. I see a square root of L effectively in the bottom. That's the same as an L to the negative 1/2 in the top. And the G here and the square root of 1 over G here does simplify to just square root of G in the bottom. Because it's in the bottom, it's like G to the first times G to the negative 1/2. Add the exponents, 1 plus negative 1/2 is 1/2. I do have effectively a G to the 1/2 in the bottom, which is the same as a G to the negative 1/2 in the top. This is correct. If I copy and paste that and switch the L to a G, then I check the derivative with respect to G and I get this. Okay, yeah, Mathematica is writing things in strange ways, but these are equivalent. You do see the negative sign. You do see the pi. L over square root of L is the same as square root of L on the top, which is what we've got there. I got the G's in the bottom, a G squared divided by square root of G. It's the same as G squared times G to the negative 1/2. 2 minus 1/2 is 3/2. And then G to the 3/2 in the bottom is the same as G to the negative 3/2 in the top. This is a strange way of saying the same answer. Okay, so I'm just confirming that it works there. Let's try an approximation now. What if my pendulum starts with a length of 2 meters? Longer pendulum than you're used to. That's like almost as tall as me. What I'm looking at here is using this formula here. Starts with a length of 2 meters. G is 9.8. Let's say we're near the surface of the Earth at sea level. And I change the length of the pendulum a little bit. How? Well, effectively by getting a new pendulum. I'm not saying the pendulum is stretchy. I mean, maybe it could be, but by changing L, I'm changing what pendulum I'm working with. I get a new pendulum that's just a little bit longer, 0.1 units longer. Delta L is 0.1. That's what I'm doing here. Let me write it by hand as well. I'm using L equals 2 meters. G is 9.8 meters per second squared. Delta L is 0.1 meters. I still need to use the same values of L and G as before for the next term. And what's delta G going to be? Should I go up a mountain? I could make delta G negative. Maybe negative 0.05. How would that happen? I go up a mountain to make the change in the acceleration due to gravity negative. What do I get when I type all this? And hopefully don't make a mistake. I get the approximate change in the period. Right, so I'd have to know what the original, I don't know what the original period is. I can figure that out. This is going to be the approximate change. About 0.078. Standard units would be seconds. A little longer period. A little slower motion by about 0.078 seconds. What was the original period? I could use the original function. The original period was about 2.8 seconds. F is giving me the period. I can double check the linear approximation by doing this. I'm making L change from 2 to 2.1, increasing by 0.1. I'm making G change by negative 0.05 from 9.8 to 9.75. Hopefully, we get a value a bit bigger than this because that's what the linear approximation is predicting. How much bigger? By about 0.08 if I round it. Hopefully, we get something fairly close to 2.92. Will we? Not a guarantee. Let's just see what happens. Okay, yeah, I guess it did round to 2.92. How about that? We got lucky. The linear approximation predicted our period would be about 0.08 seconds longer. And yes, 2.916 minus 2.83845 is about 0.08. Very close. Now you might say, well, why would you bother doing a linear approximation when you can just do this? We've got technology. Why bother with a linear approximation? That's a good question. It's a valid kind of question. I won't go into detail, a ton of detail, other than to say that what we did here can be useful in giving you quick and dirty approximations to percent changes. Essentially, by dividing both sides of this approximate equation by t itself, it can be simplified a lot and give you quick and dirty approximations to percent changes that are reasonably accurate. But you still might say, can't we still just use technology? Yeah. I will also say, though, that linear approximations are the basis for a lot of other things in math, including a lot of numerical methods that are done on computers. They are the basis for a lot of numerical methods done on computers. How are computers and calculators programmed to do approximations? You won't understand how they work unless you learn about linear approximations and more general kinds of approximations called Taylor polynomials in Calculus 2. Okay, so this is just, it's a foundation for other things, is what I'm trying to say. Okay, but it's still worth illustrating and knowing about in Calculus 1 to this level. Lots of symbols, but if you keep your head straight and don't get too worried about all the symbols, just plug in the numbers in the end, you can get the right answer.